Hey everyone, have you ever encountered this while programming? Let's say I have two variables here, x and y, where x is 0.7 and y is 0.6, and then I try to print x plus y down here. Well, we can run this and we're gonna expect 1.3, except we don't get that. We get this 1.2999 repeating. Well, that's not right, so what's going on here? Well, this is a perfect example of the nature of floating point numbers. You see, floating point numbers have a hard time representing certain numbers. The same can be said about our traditional base 10 numbering system. For example, what is 1/3 in base 10 notation? Well, it's 0.333 repeating. And we can never actually represent the true number of 1/3. We can get more accurate by adding more threes, but we're never able to actually write 1/3 in base 10. Well, this is the same phenomenon that is occurring here with base 2, and I'm going to break this down and show you exactly what's going on here. So let's jump right into it. So here we have our example 1.3, and as you saw before, floating point notation is not able to actually represent 1.3, so this is a good example. So the first thing we want to do is turn 1.3 into binary. So here we have a table to convert to binary where the left side of the decimal place is our integer side and the right side of the decimal place is our decimal side. On the integer side, we just have our 1, and on the decimal side, we have our 0.3. So over on the integer side, it's pretty simple. 1 base 10 is the same as 1 in binary, so we can just set that to 1. And over here on our decimal side, we're going to use a little trick here. First, let's take our 0.3, and then we're going to multiply it by 2. And this will give us 0.6. And on the left side of that decimal place is 0, it's 0.6. So we're just going to add 0 to this first spot. And so now we want to pull our answer 0.6 down and multiply it by 2. And 0.6 times 2 gives us 1.2. And so now we have a 1 to the left of the decimal. So we want to remove that 1 and place it in that binary slot. And so now we have 0.2, and we'll move that down and multiply it by 2 to get 0.4. And we have a 0 to the left of the decimal, so we'll set it to 0 in the binary slot, and we'll keep going on with this pattern. And so you'll notice here that this pattern will just repeat forever to try to represent that 0.3. The only problem is computers can't hold infinite bits, and your computer is either a 32-bit or a 64-bit computer, so you can see where trying to represent that 0.3 starts to become a problem. Let's convert this 1.3 into 32-bit floating point notation to really understand what's going on here. So first of all, starting from the right side, we have 23 bits dedicated to our mantissa. We have 8 bits dedicated to our exponent, and we have 1 bit all the way to the left to represent our sign bit. So the first thing we want to do before moving anything over is to move our decimal and our number to the right of the leftmost 1 in our number. And it looks like we're already in that position, so we don't need to move our decimal anywhere. Next, we can essentially just forget about that 1 and the decimal because it's always assumed to be right here when reading floating point numbers. Now let's add the decimal side of our number to our mantissa. And remember, this pattern for the decimal side is just repeating, so we will fill the rest in following suit. Over here we have our sign bit, and since it's a positive number, we'll add a 0 here. Next is our exponent, and you remember the step where we needed to move our decimal to the right of the leftmost 1? Well, if you did that, your exponent would be equal to how many spaces you moved. For example, if you move to the left 3 spots, your exponent would be a positive 3. And if you move to the right 3 spots, your exponent would be a negative 3. And since we didn't move our decimal at all, our exponent is just a 0. Now, this exponent doesn't look like a 0 at all. This is because whatever your exponent is, you'll want to add 127 to that and convert it to binary. This is a way to allow for negative exponents. For example, if my exponent was a negative 127, I would add 127 to that and get 0, so I would put all binary zeros if my exponent was a negative 127. Using this method, 32-bit floating point numbers can span from negative 127 to positive 128 for the exponent. So here we have it, all 32 bits trying to represent 1.3. The only problem is 32 bits isn't enough. In fact, no bits are enough. We would need an infinite amount of bits to continue that pattern in the mantissa. And as you can probably guess, using 64 bits will increase our precision because we have more bits to use in our mantissa. So switching back to our original example, you'll see my answer is a little more precise. That's because my computer is 64-bit. Okay, so what now? Are we supposed to just deal with this? Well, Python has a built-in library called decimal to deal with this issue. So to fix this, we can do from decimal, import decimal. Then for our x, let's do decimal, and we will enclose our 0.7 as a string inside of this decimal function. And let's do the same for our 0.6. And now we can try to run this again, and there we go. Now we have our 1.3 that we were looking for. So that's pretty much it for this video. If you have any questions regarding something I may have unclearly explained, please leave a comment and I will try to answer your question as best I can. If you enjoyed the video and or if you learned something, please be sure to leave a like. And if you like content like this, hit that subscribe button. Thanks for watching, and I'll see you all in my next video.